Hi, in this video, I want to introduce you to this toy, the Etch A Sketch, and show you how it relates to parametric equations. The Etch A Sketch was a toy invented in France by an electrical technician and toy maker, and it was extremely popular in the 1980s. And the way it works is this. You have two knobs. All it has are two knobs, one on the right and one on the left. The Etch A Sketch has a little pen behind this screen. There's a little pen. Let's say it's located right here, right now. You turn the knobs to move that pen. The thing about it, though, is that this knob on the right, you can turn it back and forth, and it only moves the pen horizontally. It only moves the pen left and right. So if I move the right knob only, then it moves back and forth, left and right. The knob on the left, and I turn it, it goes only up and down. And let's say after I turn it up and down, I end up here, and then I turn the knob on the right again, and it goes sideways again. Like, that's the basics. But if you move them both at the same time, then the pen, wherever it is, let's say it starts here, it will move depending on how you turn them, right? If you turn the right knob a lot more than the left knob, then let's say that you on the left, you turn it to go up by a little bit, but you turn it to the right by a lot, then it moves a lot horizontally, but not that much vertically, so it actually makes this diagonal sort of slanted slope. And so if you're good at it, you can draw all kinds of awesome pictures like these that I found on the internet. The Etch A Sketch also made it to the Disney Pixar movie Toy Story, the original installation. This one.
Hey, Etch, draw. Oh, got me again. Etch, you've been working on that draw. Fastest knobs in the West.
So what does that have to do with parametric equation? You could have guessed by now that this knob on the right, it only moves horizontally only. Then it indicates the motion along the x-axis. This one goes up and down only, vertical. So it indicates a motion along the y-axis. So imagine if you move the x and y equally. Let's say that you move the horizontal by whatever, 1/10 of an inch, but the vertical also up by 1/10 of an inch, then the picture you get is that little 45-degree angle. If you have very steady hands and you move them both exactly the same way, same steady speed, then you get a 45-degree angle. Well, what does steady speed mean? Steady speed means x is some, let's say, 0.1 t, and y is also 0.1 t. They are equally steady. You got the 45-degree line. Yeah? Well, someone else also has steady hands, and they do it a lot faster. 5t, and y also equals to 5t. Then what happens? What happens is that you barely got along this way, and they are already arrived over there. But if they sit and wait, eventually you will catch up, and the both of you draw the exact same 45-degree line. What about someone who has not steady hands? If I have really unsteady hands, but luckily for me, I have equally unsteady hands. I'm gonna switch my color to red. I have very zigzaggy and unstable motion on my right hand. But suppose that even though my hands are not steady, they're equally and identically unsteady. So my y coordinate, my left hand, moves at the exact same kind of zigzaggy, a copy and paste kind of zigzaggy. So let's copy and paste. So my right hand and my left hand are identically zigzaggy. But because it's still equal, what do you think happened? I start here and I go zigzaggy up, but because X and Y are identically zigzaggy, I may go up and down, but in exactly the same way. And therefore, I cannot deviate from that 45-degree line. For 45-degree, to get away from the 45-degree line, my Y has to be different from my X somehow, but it's not. So eventually, sooner or later, I guess, at some point, I'll end up at the destination. That tells you two things about parametric equations. You can have the exact same path, and you can have multiple parametric equations along it, depending on how the person is walking along that path. In other words, the traditional way of writing the equation, when you write the equation of a 45-degree line, y equals x, you are only describing the path, but you're not describing how people walk along that path. Person number one walks slowly. Person number two walks a lot faster, but they walk along the same path. So it's the same traditional Cartesian coordinate equation. Whereas person number three goes zigzaggy back and forth, up and down along the exact same path. The parametric equations allow you to describe the actual walk, not just the path. The traditional equation that you learned in algebra describes the curve or the graph, but it doesn't describe how a person or particle is traveling along that path. So you can imagine like a racetrack. Everyone is running around the exact same sort of like rectangular, curvy rectangular path. But everybody has a different parametric equation. So let's write all of that down. The traditional equation, which is sometimes written as y equals fx, or maybe x is equal to g of y, or maybe some combination, some function of x and y equals 0. For example, the equation of a circle is x squared plus y squared minus 1 equals 0. That's the equation of unit circle. Describes a curve. Parametric equations, xt is equal to some function of t, and yt is some other function of t. Same curve may have many parametric equations. All right, hope that helps with the conceptual introduction to parametric equations. We'll have a lot more math to play around with it. Any comments? Put it in the comment section below. Like, share, and subscribe for more contents. In fact, if you have any questions on parametric equations and you want me to make a video about it, put it in the comments as well. All right, thanks for watching. Bye.